for the introduction. I'm Tommy's colleague. That's how we... And I promise that I'll be on time. Those of you who are familiar with the name Bischof-Niemz, that's my wife is the conference organizer, so I promise that I'll be on time, otherwise I'll get problems at home. So it's a great pleasure to be... I'm delighted to be to give the first content-wise presentation after these very inspirational talks that we had in the morning about the 100% renewables vision. And if we want to plan 100% renewables or a large renewables energy system, it all starts with the resource. We need to understand the resource well. The solar resource, the wind resource, and of course on the wind side it's a bit more tricky to assess the resource, because the wind we harvest in 100 meters above ground, and it's a bit more difficult to assess that and to model that than the solar resource which we harvest on ground. So with that, I would just like to give you a little bit of background around the study and the methodology that we use. I want to highlight to you the wind potential in South Africa, where we stand and what we found in the study, and talk a little bit about wind short-term fluctuations in South Africa as well. Maybe the first background before I go into the details of the study is this slide, which shows you in the South African context how rapidly both solar PV and wind have reached full cost competitiveness in just 4 years. What you see on this slide is the outcome of the Department of Energy's competitive procurement program, where the Department of Energy buys solar, wind and other renewable electricity from independent power producers. And this whole program started in 2011 with bid window 1. And there we had on the wind side an average tariff of £1.51. That's roughly in euros around about 9 euro cents a kilowatt hour. So even for the first round also not that bad. But then very quickly, in the last bid window that was submitted last year in November 2015, we are now at 62 rand cents per kilowatt hour for new wind turbines. That is now in euro terms below 4 euro cents a kilowatt hour. So very, very competitive. And if we compare this to the alternative cost of new power generators that we have available in South Africa as we speak today. Now, solar PV and wind are by far the cheapest new build options that we have available in the country. We are looking at these 62 cents for both new wind and for both new solar PV. And the next cheapest is a baseload coal-fired power station, which was just awarded 3 weeks ago, also an independent power producer, also a tariff-based contract with the off-taker Eskom, so exactly the same risk profile as the solar and the wind projects, and that baseload coal-fired power station came in at a tariff of £1.03 a kilowatt hour. So solar PV and wind now 40% cheaper than new baseload coal in a country that has one of the cheapest to harvest coal resources in the world. And still solar and wind is 40% cheaper. Now, with this introduction, just on the cost side, let me tell you a little bit about the study that we did. We conducted a joint study together with Sanedi, Eskom, our public utility, and the Fraunhofer Institute to holistically quantify the wind power potential in the country across the entire geographics of South Africa, and to measure and quantify the portfolio effects of having a widespread spatial aggregation of wind power across the country. We used what we've mentioned before already, the Wind Atlas South Africa, a very successful program that has run for a couple of years. Technical work there conducted by the Danish Technical University, and the DTU also reran the WASA model in the context of this study that we conducted. So that database is actively being used. The entire results of the study, I will just highlight like I will just point out the highlights, but the entire study you can find on our website behind that link. Now, when we started with the project, we had the WASA program is of course ongoing, and the WASA program is constantly increasing the coverage of the so-called WASA domain. But when we started last year with the project, we had this WASA data, or this map available in very high resolution, 250 meter resolution, a very good assessment of the wind resource, but only mostly along the coastal area of the country. So we said, well, if we wanted to go for very high renewable scenarios, deep decarbonization, we need to know what does the wind resource look like across the entire country. So what we did, we reran the meteorological models that lead to these wind speeds, and we reran it in a resolution of 5 by 5 kilometer resolution for a 5-year period from 2009 to 2013, and in 15-minute temporal resolution. So now we have wind speed data that covers the entire country. In this 5 by 5 kilometer resolution, roughly 50,000 individual squares covering the whole country, and for 5 years from 2009 to 2013 we have 15-minute time series of how much wind speed do we have at 100 meter above ground across the entire country. So now you can see that South Africa has in very wide parts of the country, not only the coastal areas but also the inland parts, have wind speeds that are 7 meters per second or above. Now, 7 meters per second, is that a lot? Is that not a lot? It's always good to put something into perspective and to compare it with something that we know. Because of my accent, you can tell I'm from Germany, so I used the German example to compare it. And Matthias will see the difference in the wind resource potential immediately, because he makes money with wind turbines in Germany. So you see on the same scale, the yellowish part in South Africa is much wider and much higher than in Germany. So it's essentially most of South Africa has the same wind speeds that Germany exhibits in only the northern parts close to the coast. And yet Germany has an installed wind fleet of 46 gigawatts. Now, the wind speed map is one thing, and it's great to see a wind speed map and to see what the average wind speed over a 5-year period is. But when it comes to wind specifically, there's a very high non-linearity between the wind power as an input, the wind speed as an input, and the electric power output as the output. That's other than for solar. In the solar case, typically, if your solar radiation doubles, you get more or less twice the power output from a solar panel. There are some second order effects, but in principle that's true. For wind, that's not the case, because the power curve of a wind turbine is highly nonlinear. Once you reach your 10 meters per second, the wind turbine runs at its maximum rated capacity and it doesn't increase its power output any further. So we have to take the wind speed map and translate it into something that is more meaningful in the power sector, which we then call a capacity factor map, where we model how a wind farm would produce energy in the different 50,000 pixels, and what average capacity factor would that simulated wind farm have produced from 2009 to 2013. In order to do that, because not every wind turbine is best suitable for each and every place, it depends on the wind profile, we defined 5 different generic wind turbine types, all the way from a so-called high wind speed turbine that has a relatively low hub height and a relatively small blade diameter, so it's suitable for very high wind speeds, all the way to a low wind speed turbine with very high hub height of 140 meters, and a much larger blade diameter, so it has a larger swept area in which it collects the wind energy. Now, just worth noting that all these wind turbines are completely off-the-shelf products, and 140 meter hub height is not something that we just dreamed up, and it's not being implemented. This is off-the-shelf and standard way of implementation in many European countries at the moment. If we take these 5 different wind turbine types and now put the best suitable wind turbine on each of these 50,000 pixels, this is the distribution that you will see of how we place the wind turbines across the 50,000 pixels. Where you see the areas with the very high wind speeds, that's where we put turbine 1 and 2, there's some of the 3s, but most of the country is covered with the turbine type number 5, the 140 meter hub height turbine. Now, when we now look at the results, so what we, sorry, but I jumped this one. So, and then we applied for each of the pixels, we now applied the wind farm power curve to convert the wind speed data that we have for 5 years, to convert that into power output, and then to measure what the average electricity production would have been in that pixel with that wind turbine. So these are the power curves that we applied for wind turbine type 1, wind turbine type 2, and then 3 to 5. And the difference between the upper part and the lower part is that the upper part is the power curve for one individual wind turbine. Here you see the high non-linearity with constant output once you reach the nominal rated capacity. And then the the power curve for a wind farm that we model for each pixels is more smoothened because we are not looking at one individual turbine, but we look at 50 turbines that we place into one of these pixels, and you have a smoothing effect there. And now if we apply that and now we've modeled the electricity output across the country, now we get to a very different map. We get to the capacity factor map, and that's how this capacity factor map looks like. This now tells us what in each of these 50,000 pixels, what capacity factor would we or could we have achieved in this 5-year period from 2009 to 2030. And now anything that's yellow or red is a capacity factor higher than 30%. Again, it's only meaningful if you compare it to something that makes sense to us. If we put the actuals of Germany, Spain and the US next to that, Germany, the German wind fleet runs at roughly 20% capacity factor, the Spanish fleet slightly better, 25%, the US fleet on average runs at roughly 30% capacity factor. So you can see how good the resource in South Africa is if we compare it to the achieved capacity factors in other countries, where we can achieve up to 40% for inland onshore wind turbines. That's a very high capacity factor to achieve. If we now say, okay, we went up to 140 meter hub height, and to be fair, a large part of the German, of the Spanish wind fleet and the US wind fleet, they don't consist of 140 meter hub height yet, because it was not installed 10 years ago, but only in recent years. So if we limit ourselves to 100 meter hub height, which was completely standard even many years, a number of years ago, if we limit ourselves to only turbine types 1, 2 and 3, and we still have a similar picture, we still get into the yellow and red in very, very wide areas across the country. So from this we conclude, that's why the title of our presentation as well, we all know that the solar resource in South Africa is very good, and we are all happy to be here in a time of the year when I assume in Europe the weather is probably very bad. So that's pretty clear, but the wind resource is basically on the same level as the solar resource in the country, and we have a lot of space as well in the country, very wide areas where we can achieve high load and capacity factors. If you do a little bit of statistical analysis on that, on these numbers, put the achievable load capacity factor on the x-axis, and plot the percentage of the South African landmass that can achieve that capacity factor on the y-axis. Now you see the numbers that I mentioned from the map before already, but now you see them as actual numbers. So if we now take a 35% capacity factor as a cutoff point, and it's a very high capacity factor to build a commercial wind farm, we take that as the cutoff point and we limit ourselves to only turbine types 1, 2 and 3, only the ones that go to 100 meter only, then we still have more than 50% of the entire South African landmass that can achieve that capacity factor of 35%. That is a very good wind resource in total. If you put the installable capacity, which scales with the same with that on the y-axis as well, the installable capacity, if we do that, if we only install 35% capacity factor turbines, we would be able to install 3,500 gigawatts of wind turbines if we use each and every pixel. Of course, that's completely hypothetical, we would never do that, but just to put the magnitude of the potential here. That's by the way, a wind fleet that would be big enough to power the entire world. So it's clearly not what we will do, but it's always good to put some numbers into perspective. Again, if we put these achievable capacity factors and compare them with what is already being achieved in other jurisdictions that have very high wind fleets, the US again with 74 gigawatt up and running, Spain 23, Germany 46 gigawatt, and these are the ranges of achieved capacity factors in these countries. And here you see for the different wind turbine types what the minimum and the maximum and what the bandwidth is that we have modeled that is achievable in capacity factors across the country. And it's literally only the very, like the worst pixels, let's call it, across the country, turbine type number 5 on the very right. There you see that this box plot is the minimum in these very low wind speed areas is still in the range of what the average German fleet produces. Now that was the one question that we wanted to answer. What does the wind resource actually look like? And we can safely say that the wind resource is really excellent in the country, and that's just the link to the 62 cents that we saw in the beginning. That's completely confirmed by the Renewable Independent Power Producer Program's tariffs as well. If we look at the short-term fluctuations of the wind fleet, which is always a concern of system operators, or I should say not always, not of the system operators that are already dealing with it, but the ones where it's new, where we hear 4% is the maximum that can be introduced, and that number increases decade by decade. So we wanted to quantify from the word go, from the start, how do the short-term fluctuations actually look like, and how do they change if we spread wind farms across the country. In order to do that, we ran a lot of statistical analysis here. I just want to show you, for illustrative purposes, one specific day. So that's the 14th of January 2012. And what you see on that animated map, let me run that again, you see how the wind speed moves across the country. And on that plot on the right, you see the power output, the simulated power output of a wind farm that is sitting in this pink pixel. So on that day, the day itself, during the day, it was quite wind still, so the wind farm was producing at 90% of its rated capacity at midnight. Then it dropped to 0 output, and then in the early afternoon it picked up again and went back to 90% of its nominal capacity. On the lower graph you see the 15-minute gradient, so it's just a time derivative of the upper graph to tell us what percentage change do we see within 15 minutes. So for one individual wind farm, yes, the gradients are quite always run and operate at the rated output that you expect, because something unforeseen might happen. Now, in summary, with this very first presentation talking about the wind resource in South Africa, what have we learned? What did we not really know, or only we had a feeling before we did the study, and now we have the hard facts for it? Before we collected the data, well, at least the perception was, probably not in this room, I know this room knew it 5 years ago already, but or probably even before that, but many people in South Africa were of the opinion that the wind resource in South Africa is not good. And now we show that the wind resource in South Africa is actually on par with solar, so we have two very good non-deployable resources. Secondly, there's not enough space in South Africa to supply the country with wind power. Well, there is clearly, in such a large country as South Africa, more than enough space, and such a large country that is gifted with such a high wind resource leads to 80% of the country's landmass has enough potential to achieve 30% capacity factor wind turbines. So we can safely say the technical potential for wind power in the country is completely unlimited. We have to direct where we want to install, of course, but it's our choice where we install, and we can install as many wind turbines as we need to power the country. Wind power has very high short-term fluctuations. Well, yes, on individual wind turbine level, that's correct. On portfolio level, the 15-minute gradients are very low. Lastly, wind power has no value because it's not always available. Well, even on portfolio level, there are times when the entire wind fleet that we simulated does not produce power output. That is also a correct statement. However, on average, wind power is the power generator if you compare it with solar. Solar is like a 9 to 5 office worker. It works just during the day. And wind power is your 24/7 3-shift worker. And for any good 3-shift, you have varying output. It's not always the same, but it's in principle a 24/7 power generator. And that's what makes solar and wind so nice and complementary, because they have their very distinct advantages. The one being available all the time with varying outputs, the other one only during the day with a more stable, more predictable output. So if we mix these power generators, and we will have a more detailed presentation about that tomorrow morning, but if we mix wind, if we mix it with solar, and we mix it with flexible, more expensive power generators, we can produce any form of demand profile at lower cost than the alternatives that we have available. All these analyses are being continued as we speak, but for now I thank you very much for your attention.